Today in our talk, I'm going to show you how we managed to achieve such a scalable testing infrastructure. Okay. We will talk about the past, which includes also logs and screenshots and might seem trivial. We also going to talk about the future, which includes machine learning algorithm, and might seem complex, but don't worry. If you're new to machine learning, I'm going to do a little bit of a machine learning basics tutorial and show it on our example. So I hope you find it interesting. If you are familiar with machine learning basics, I hope you find it even useful. And if you are expert data scientist, please come to me after this talk. I have some questions for you. Okay, so let's start. Automation Engineering Guild. We are 21 software engineers located in Ukraine, but mostly in Tel Aviv. We divided to 3 different teams, each team responsible for different projects. So what do? We develop velocity services and tools for the R&D group. If you sit in here, you probably use them, some of them, whether you are aware of it or not. But we also, of course, have our amazing testing infrastructure. We have our Selenium test that run on TeamCity, can also run on a browser stack or Sauce Labs. We also have our new infrastructure that we work in with the feds. We're using Puppeteer, and we're running on AWS Lambda, which is super cool. But today, we will talk about our E2E Java infrastructure. Okay, so we're talking about E2E. It means that we open a browser, we use Selenium, we open a browser, we click, and we verify things on the test. Our test support, our infra support more than 20 different projects, right? You can see the projects here. It's used by around 60 QA engineers. If you don't know, the QA engineers are the one that writes the test, run it, analyze it, and manage the whole test. We support the infrastructure. We run more than 10,000 tests. We have more than 10,000 tests, and we run more than 200,000 test runs per day. So it's pretty amazing. In 2013, we had around 1,000 tests with 5% failure, which is okay. In 2018, we have 10,000 tests with 3% failure, which is even better. Okay, so it used to be a Borat image, but we don't have the copyrights for it, right? So I needed to put her. She's free. She's legal. Okay. So it used to be not joke. Okay. Let's see why not. So if we have 10,000 tests and we have around 3% failures, it means 300 failed tests. Okay? If it takes around 3 minutes to debug a test, it requires 15 hours to debug, which means 2 dedicated people every day. So we can see even we're doing a good job, but it's still we need to improve it. Okay, so as you understand already, our main goal is to achieve scalability, right? And when we're talking about scalability, there are few major issues we always need to solve. Okay, when we're talking about testing infrastructure scalability, the main 2 we have more, but the main 2 are we want to increase the success rate. We already saw that 3% failure can get messy. Okay, so we want to increase the success rate, and we also want to reduce the analysis time. Okay, which is super important. And in our talk, I'm going to show you how we did those things. Okay, in the past, in the present, and in the future. Okay, so let's start. Past, 4 basic methods, okay? Of course, we did a little bit more than 4 things to improve our scalability. And then you can see the wooden robot here. So it was in maybe 5 years ago. They're pretty, I don't know, pretty easy to implement, and you can use it for your integrations or your units even. So let's start. The first method, we can see here, there is a test, okay? We can see by the annotation, it's weeks test annotation. It means it runs on our infrastructure. You can think of it as just test annotation of JUnit, but we just store some information like who is the owner and some other stuff we can store. You can understand by the name that we verify if the text is underlined. But other than this, it's pretty hard to understand what's going on here, okay? And if you are QA engineer and you have 40 or 50 tests to analyze before you can release a version, it's going to take a lot of time, okay? So the first thing we did is adding user steps logs, okay? So it's very basic, and the logs, we write the logs on TeamCity and on a local machine and whatever we want. So let's read the logs. So we can see we add a title, we open the panel, we click on underline, and we verify that the text is underlined. Now it's easier to understand what's going on in a test, and if you're a QA engineer and you want to debug it, you can just debug it wherever you want, right? There is still something fishy here. It's the assertion. We can see that it's just we assert we need to write the text, right? In the next test, we will probably duplicate it. And in general, it's just not readable, okay? So the second thing we did is we, of course, user logs reduced analysis time. We changed the assertion structure, okay? So now every element, again, we're talking about E2E, so we have web elements. Every element can assert on himself. So what's the size, what's the color, and in our example, the style property is underlined. So also, we reduced analysis time, and it's pretty easy to do this. Our next method was failure screenshot. Okay, pretty easy to understand. Every time the test fails, it takes a screenshot and display it on TeamCity. You can see here that we clicked on the underline button, but there is no underline. So we understood just in 3, 4, 5 seconds that we have a bug here. Very easy, very common tool, very easy to implement, and very, very useful, and of course, reduced analysis time, okay? Our last method from the past is failure video. Same thing, just with a play logo. Okay, every time a test failed, it will take a video, and you can just watch it in TeamCity. Usually we do it when we have issues in the middle of the flow in the test. Just can watch it, and it helps, of course, reduce analysis time. So this was in the past, maybe 5 years ago, 6 years ago. Help us to get maybe to the 3,000, 4,000 tests. So the present, okay, this is actually, we started working on it maybe 2 years ago, really helped us to achieve scalability. We're talking about around 10,000 tests, and we even can get us to the 15,000 tests. Automation manager, which implement the test state pattern, okay? So let's see what it is. So the main idea behind the automation manager is to store two kinds of entities, okay? One is test entity, and the second one is run result entity. And as you can see, they have one-to-end relationship, which means every test can have a lot of run result, okay? Let's have a look at the run result and with the data that we store. So we have some basic information like the test name, if the test passed or failed, when was it happened, and version and experiment, and a lot of other configuration that we store. But the most important ones that we will use in our machine learning phase, so pay attention now, it's the exception message. Okay, pretty easy. What's the exception message? And test duration. And I think most important one is the build pass rate, which means how other tests behaved in the build. Okay, if it's a number from 0 to 1, if it's closer to 1, it means most of the tests in my build, in my configuration, failed. Sorry, if it's closer to 1, most of the tests passed. And if it's closer to 0, most of the tests failed. So it can give me a better look on what happened in my configuration, which is very important data, and we will use it in the machine learning. But let's have a look on the test entity. Also store some basic information, like what's the name, when this test was created, who is the owner, special annotations, if there is a Jira task that describes this test, right? But the most important field is the test state, okay? This is actually the main concept of Automation Manager. So let me show you what's the test state. So maybe saw it before. Basically what it means is that we want to separate the stable tests from the unstable test. Okay, and if we can separate them and run them separately, we can really increase the success rate. So basically, test state pattern means that every test have a life cycle, okay, and each state in the life cycle reflects on the stability of the test. So let me show you an example. When a new test was created, it will start as a beta test, okay? It runs separately from the stable one, because usually new tests are not very stable, okay? There is something called element timing issues, which we'll also talk in soon, when it means that we try to click or perform an action on an element, but the element didn't render fast enough. So usually it happens in the new tests. So we run in TeamCity, we run the beta test separately every night, and after it passes X times in a row, in our system it's 30. So after it passes 30 times in a row, it will move to stable, okay, and can run with other stable tests, which is the best scenario we want, okay? But sometimes a test is not that good, and if it don't pass for X times in a row, after Y days in our system is 2 weeks. So after 2 weeks, it will move automatically to failed beta. Okay, failed beta is kind of the graveyard of our test. Okay, and it means that we usually don't run those tests, and it requires a manual fix, and it means something is wrong there. So after we fix it, it will go back to beta and start the process all over again, okay? Sometimes a stable test can become unstable, okay? When we identify this behavior, we automatically move it to flaky, okay? It usually causes, again, because of the element timing issues, elements start rendering slower on our agents, and we just try to perform an action before it's rendered. And we get flaky one time it's passed, one time it fails. So also we run it separately from the stable and run it every night, and when it will pass X times in a row, we'll move back to stable. So this pattern helps us to separate the stable from unstable test, and now every QA engineer can, with a simple environment variable, just choose what states he wants to, which states he wants to run. Usually it's the stable, sometimes also the flaky, yeah, and just take care of the good test, and when you try to release a version, okay? Of course, this helps us to increase the success rate, okay? This is the UI. I know it's not stunning. It was in a guild week. But as you can see, this is Heli. Heli is here? OK, so we can talk about her. It's fine. So this is Heli's dashboard. You can see the tests. We have some other stuff that we didn't talk about, but you can see that she has 2 beta tests and 11 flaky. okay, and 55 stable. So in overall, she's 81% awesome. Okay, she will be 100% awesome when all the tests will be stable. Heli is 100% awesome for us, but for the manager, she's only 81%. And you can see here she can filter her test and debug them from here. Even, I don't know, just go to TeamCity. We have a link here to the TeamCity run and to actually debug it and do whatever she wants. Okay. Yeah, you can choose not to run with the automation manager. Okay, when usually it's a new project and we work on it and there are a lot of changes, we decide not to run this project on the automation manager. But let's say editor, Wix code, ADI, everything is running on with the automation manager, and you can just turn it off. Again, it's environment viable in TeamCity. Just turn it off, and everything will run. So it's your choice. This was the present, what we worked maybe 2 years ago. Help us to get to the 10,000 and even more. But now we're going to talk about the future. Okay, so the future includes machine learning and failure classification. So failure classification, again, we're talking about E2E tests. Okay, and E2E tests can have many, many issues. But the most common issues that we actually working on to classify are element timing issues, what we talked about, that the element didn't render fast enough. Loading issues usually happens in the few first seconds, and maybe integrating with TeamCity or just initializing the test. And we have also dev changes, which is a little bit more general one. Selector changes, new features, and production bug. Okay, this usually require someone to have a look, and those we can easily fix. So if we want to specify better the problem, we want to get run result as an input. And remember, we have automation manager that store all this run results, so we have the data, and we want to get the failure type as an output. Okay, so this is our problem, and we can solve this in many ways. Okay, but because we have so much data from the automation manager, and because it's super cool to use machine learning algorithm, we decided to have a learnable model. Okay, so a learnable model, basically it's a machine learning algorithm or a series of machine learning algorithms that will improve in time and with more and more data. Okay, and I want to explain what we're doing exactly, but I need to talk to you, to explain you a little bit in machine learning basics, and I will show it on our example. So machine learning, I can assume that you understand the basic concept that you need data to improve your algorithm and to learn from it, okay? Or to predict a value or to extract knowledge. So data, you can think of it as a table where the rows also called samples, okay? And the property name also called features. So this is the data that we use. We can see that the feature can be either a class or a type. Here it's low and high, okay? Just a known list of possibilities. And also it can be a numerical value, a number. Also, of course, it can be pictures, images, unstructured string, but we won't talk about them today. We will talk about simple features that we actually use in our problems, so it's fine, so it's good. There are two main types of machine learning algorithm, okay? The first one is called supervised learning, okay? Supervised learning is when you want to predict a value. So I think that when you think about machine learning, you always think about supervised learning because this is the most common type. So there are two types of values, okay? The first one called regression problem, which means we want to predict an actual number, okay? Like what will be week stock next week, okay? So we can predict it. Also, we have classification problem where we want to predict a class or a type. So if we're talking about weak stock, so if it will go up or down, but won't give me the actual number. Okay? In our problem, we try to classify one of those types. Okay? We already talked about them. In order to be able to learn something, we need to give labels. Okay? Labels, you can think of it as a special features which hold the correct answer for the sample. Okay? And the algorithm will take the label and learn from it for a new sample. When a new sample will arrive, it will use all the other samples with their labels and will able to predict a value. Okay? So when we're talking about regression, you can see the label is, of course, a number, because we want to predict a number. So the label has to be number. If we talk about classification, you see that the label also is a class or type. So here it's increase, decrease, or whatever you want, a known list of possibilities. In order to label, it requires a human effort. Okay? Usually, someone will label the samples, even though we can do it automatically, and I will show it in a second. We need someone to label them. And of course, because we want to predict a value, we need to understand, or the model needs to show us how good it performed. Okay? So accuracy prediction. Okay? So we want to say how good the model is. The second type of machine learning algorithm is called unsupervised learning, and it's less common, usually require mathematical or statistical knowledge. And usually its purpose is to extract knowledge and not to predict a value. Okay? So supervised learning predicts value, but unsupervised extract knowledge. Usually it helps, we're doing unsupervised learning to help the supervised learning to learn. So, what it means to extract knowledge. So we have clustering problem, which means we don't have labels, we only have the data set, and we want to cluster it, okay, to split it into groups, different groups. So if we have this data set, which every point here is a sample, and it has only two features, okay, which are, in this case, numbers, okay, it's a numerical features. So a clustering can just split them into 3 different groups. So how many groups will I tell him, all right? So this is a clustering problem, and it can help you to label. If you know there are 3 groups, it can help you label your supervised learning. Also, extract knowledge means transformation of the data. So just to change the way the data looks, your sample, how they look, and usually it will help the supervised learning to perform, to give better results. So maybe to change, to remove features that is not needed, or to combine features, or to remove maybe samples that are noise, okay, and not correct, and a lot of stuff that can help supervised learning. But we won't focus on this today. Of course, unsupervised learning don't need labels, okay, because we don't predict anything. So also we don't need human effort to label, okay? And also it's hard to predict accuracy because we don't predict anything. So we actually need, the human effort that we need is the person that runs this unsupervised learning, and he needs to tell if it's working or not. So it can't predict anything. So this is unsupervised learning. But let's go back to our failure classification. Let's have a look on our data set. Okay, this is just example. We have more features than this. But the features, those features we already talked about. The exception message, right? Just the failure message. The test state, if it's beta, flaky, stable, and so on. The build pass rate, again, it's a number from 0 to 1. When it's closer to 1, it means most of our tests passed in the build, or other tests. So it can show the behavior of the build. And duration, how much it took to fail, it's all failures. And the label, of course, we're talking about classification, so it's supervised learning, okay? So we're talking about classification, we need to label those samples. So we can see we have a stable test that has element is not clickable exception. We can see around half of the test passed and the other half failed in the build. And we label it as dev changes. Okay, it was actually a bug, but dev changes, it's a general label. We also have the assertion, the beta test, the new test, that had the assertion failed, okay, with the visibility is not as expected, okay? We expected something to be visible, but it's not. You can see that most of the other test passed in this build, and we label it as element timing issue, okay? This element didn't render fast enough. The last one is another stable test, with test API is not defined exception message. You don't need to understand what's test API. It's a service that we use, but you can see that all the other tests failed in this build, and it took 5 seconds. Okay, it's in milliseconds, and we label it as loading issues. Okay, this is 3 samples of our data set. Now I'm going to show you an example for a machine learning algorithm. Okay, this is pretty simple machine learning algorithm. It's called decision tree. Come in many variants, but I'm going to show you the simple idea behind it. So basically, I'm going to show you now the result of the algorithm, the model that it gave us, and then I'm going to show you how it did it. The main idea is just to split the data into yes and no question, like is this value is like this, or is this value is under or equal to this. And let's see an example on our data set. So when a new sample comes in, it will ask it, is the duration is under 8.7 seconds? Okay, if the answer is yes, the model will classify this sample as loading issues, which makes sense because it happened in the first 8 seconds of the test. Okay? If the answer is no, it will ask another question. If the state is stable, okay? If the test state is stable, if the test is stable. So if the answer is yes, the model will classify it as dev changes, which also makes sense because if the test is stable and it fails, so maybe it's a dev changes, okay? Maybe it's a bug or something was changed. But if the answer is no and the test is not stable, maybe it's flaky, maybe it's beta, there is maybe a problem with the timing, okay? The element didn't render fast enough. Of course, this is only a decision tree of 3 samples. When we're talking about machine learning, we're talking about 100,000, even millions of samples. You can see that it gives another result, okay? Almost the same, but he asks also, if the build pass rate is under 0.7, okay? If it's yes, it means that it's lower than 0.7, and it means that we label it as dev changes, okay? Because if most of the tests failed, maybe something is wrong here. But if the answer is no and most of the tests passed, maybe this is a problem in specific test and it's element timing issues. Okay? So this is the model that was created from the algorithm. Let's have a look on the algorithm in, I don't know, I have maybe a few more minutes, so we can't actually dive in. The decision tree algorithm will ask question on the data. You can see here again a data set of many samples. You can see, of course, it's supervised learning, so there is labels. So we have blue dots and we have green dots, and we want to classify it. Okay, the algorithm to classify it. So the decision tree will ask the most informative question every time to be able to separate the data. So we can see that here, this is the most informative question that he can ask. Okay? And you can see it doing pretty good job. You can see all those blue dots were labeled as blue. Okay? And those green dots labeled as green. Of course, it's not perfect because those two labeled as blue and those blue dots are labeled as green. But this is with only one question. Okay? You can see here we have the second question. Second question if it's yes, or second question if it's not. And you can see here we're doing much better job. This is the 5th question and 10th question. And you can see whenever we ask more and more questions, we perform better on the training set, on those specific tests. It's not always will be the case. Okay? So this is basically how the algorithm behind is doing. Accuracy prediction. So how we can understand if we're doing a good job or not. So we have the data set, and we said we need to train the data set to get the model. Okay? If we want to measure the model, we cannot use the same samples that we use to train the model. Okay? Because the model, he saw the samples before. He already remember this the samples. So we cannot use the same samples. This is wrong. This is not good. Okay? So how we can check with a new sample if a new sample comes in? So the very basic approach will be to split your data. Okay, the data set that is already labeled into 2 different sets. Usually we'll split it randomly, but again, it depends on your problem. We'll split it to train set and test set. Okay, with the test set, we will train the model, and with the test set, which is new to the model, we will measure the model. Okay, and because we have the actual labels, that is the correct answer here, and we get the predicted labels from the models, we can compare them, right? And if we compare them, we can understand how accurate we are. So this is very simple calculation, right? The number of correct predictions divided by the total size of the test set will give us around the percentage that if we're good or not. Of course, this is a very basic approach. They are much more complicated if you're looking for false positive, false negatives, and so on. What's important in your business usually. The cool thing that you usually don't need to implement anything because there are also already frameworks that you can use that implements all the algorithm. Okay? So you only need to collect the data and label the data if you're talking about supervised learning, and just bring it and just use it with one of the frameworks there are, okay? So usually if you're a data scientist, you use Python or R, okay? Scikit-learn and TensorFlow are maybe the most common libraries in Python. It's very, very good to use it when you're trying your POC phase, okay? But it's a little bit harder to integrate it to your service, okay? This is why we have Scala, and we have Spark libraries. If you know Spark, it's also very fast. You can put it on multiple systems, and it can run millions of samples. So yeah, you can usually you start with Python or R, and then move it to Scala. So where do we stand now in these days? Of course, again, we're talking about classification problems, supervised learning. We still label samples. We have a lot of data, but it's not labeled. We use the QA as expert and to label our data. We also have, we're working on the decision tree. We're actually working on random forest, which is a little bit, it's an improvement for decision tree. It's regression classification. It's a different algorithm. We didn't talk. It's not the regression that we talked about. It's also a classification problem. And in the end, maybe when we have enough data, we can use neural network, which you probably heard about it, and it gives this small, it can tell you small insights about features and their relationships. So it's very powerful tool. We're also going to do unsupervised learning to help us label the samples and to do transformation of the data. As I said, it will help our supervised learning to learn. So maybe some features we don't need, and maybe we need to remove noisy samples. We're now working with Python because it's very good and very easy for the POC phase. But of course, when we want to integrate it to our service, we will use Scala. Okay, it's harder to integrate Python. And basically, that's it. We talked about the past, the present, and the future. And I was Sharon, and thank you, everyone. Sir, again, the Borat girl.